two-centered compound curve is a special type of horizontal curve, and this occurs when you have two simple curves placed back to back with different values for the radius. So similar to a simple curve, we have a point of curvature and the point of tangency, but our new point is now the point of compound curvature, and that's where those two simple curves meet. We have two possibilities, one where the larger radius is by the PC and one where the smaller radius is by the PC. We'll use the subscript 1 to denote characteristics of the larger radius curve and the subscript 2 to denote characteristics of the smaller radius curve. So we'll carry that throughout all of our images and our calculations. Subscript 1 and 2, the larger radius. So anytime when the value of the radius is larger, that curve gets the subscript of 1. So we have R1, and again, it doesn't matter which order the curves come in, we're looking for the larger radius, and R sub 2. We also have delta 1 and delta 2, denoting those angles for each of those respective curves. All right, zooming in a little bit so we can look at some more of these features for the curves. We can add our individual PI points for each of the curves. We have the overall point of intersection, the PI, for our compound curve system. Then we have the points of intersection for each of the individual simple curves, PI1 and PI2. And similarly, the angles delta 1 and delta 2 are here as well. When we're using a compound curve, one of the important values that we need is our tangent distance. T sub b and T sub a are the values that we're going to use, and we'll see as we go through this derivation, as we're deriving these equations, we're going to look for T sub b in the case on the left and then T sub a on the case on the right. And we'll see at the very end when we bring this together how the T sub a and T sub b fit in the larger context of the compound curve system. But this is what we're looking for the derivation. So adding in some more geometric components here, we're going to end up using the important characteristics of x1, y1, and x2, y2. And these are formed with a 90-degree angle here, and it's going to help us solve using geometry for T sub a and T sub b that we're going to use and need for our compound curve system. So starting with the case where we have our larger radius first, a larger radius close to the PC. x1 is equal to r1 times the sine of delta 1 plus r2 times the sine of the intersecting angle, and the intersecting angle is always delta 1 plus delta 2, minus r2 times the sine of delta 2. We can simplify this into x1 equals r2 times sine of I plus r1 minus r2 times the sine of delta 1. So that gives us our x1 component. For y1, we have r1 times 1 minus the cosine of delta 1 plus r2 times cosine of delta 1 minus r2 times the cosine of I, that overall intersecting angle. We can simplify this to y1 equals r1 minus r2 times the cosine of I minus r1 minus r2 times the cosine of delta 1. For T sub b, this is equal to y1 over the sine of the intersecting angle. And now we come up with our T sub b equation, r1 minus r2 times the cosine of I minus r1 minus r2 times the cosine of delta 1 all over the sine of the intersecting angle I. Now looking at the situation when we have the smaller radius curve first, we're going to solve this similarly, and we're looking for, ultimately, after we solve this, for the T sub a. So that's the tangent going from the PI to the PT. So x2 equals r2 times the sine of delta 2 plus r2 times sine of I minus r1 times the sine of delta 2. Simplifying that to x2 equals r1 times the sine of I minus r1 minus r2 times the sine of delta 2. Now solving for y2, which equals r2 times 1 minus the cosine of delta 2 plus r1 times the cosine of delta 2 minus r1 times the cosine of I can be further simplified to y2 equals r2 minus r1 times the cosine of I minus r1 minus r2 times the cosine of delta 2. We know using our relationship here, geometrically, t sub a equals y2 divided by the sine of the intersecting angle I. So ta equals r2 minus r1 times the cosine of I plus r1 minus r2 times the cosine of delta 2, all divided by the sine of I. So taking that information now, looking at a bigger picture at these two center compound curves, we have t sub a and t sub b on each curve, whether the large radius is by the PC or the small radius is by the PC. The t sub b is always associated with the side of the curve with the smaller radius. So you'll see on the left example, the t sub a is between the PC and the PI, and then from the PC to the PI on the image on the right is t sub b. So we've got to know which one we're solving for, because when we're dealing with stationing on a horizontal alignment, we always need that distance, the tangent distance between the PC and the PI. So we need to know if you have the larger radius first, you need to be solving for t sub a. If you have the smaller radius first, you need to be solving for t sub b. Those are the two values you'll typically use, especially when you're calculating the stationing for your horizontal curve. So in summary, our equations, we have an equation for t sub a, and you'll want to solve for this when the larger radius is by the PC, because you'll want that tangent distance for your stationing. You may also want the t sub b, but for stationing purposes, you're going to need that t sub a. And then when you have the smaller radius by the PC, you're going to need to solve for t sub b, and this is the equation for that. So this is how we derive those two equations for tangents, t sub a and t sub b, for a two-center compound curve.